Okay, welcome to chapter 5. This is on support vector machines. Now I think you've already seen support vector machines in an earlier course, but we're going to kind of just review them and use them as another example to see how we set up machine learning systems, because they're commonly used in machine learning systems, and they're a good simple example of how we can do this. So we'll go through this notebook here. The first thing we're going to want to do is introduce our data set. We'll be using our iris data set. We'll try to use this a number of times because then you get kind of familiar with it. So we'll use the same data set again. We're going to import these libraries. So I'm going to run this code here to import all these libraries. And then we're going to read in the actual iris data set. Now there's a couple of places that this is stored, including in the scikit libraries, but I have a version of it out in GitHub that I like to use, so I'm going to do that. Now I'm just going to hit Shift Enter to read that in and to display that top part. So we've read in this data set, and again, remember this is a bunch of flowers. And each one we have a sepal width and length and a petal length and width, and then what species that flower is. And there's 3 different species of flowers here. These are our 3 different species here. Okay, so that's what we have. We've read that in. Now we're going to set up our database here. And again, we've got we're just going to set up and use these standard variables. X is our inputs, a capital X, and a lowercase y is our outputs. And we're actually going to break this up into some training and some testing data. 80% of the flowers will be used for training and 20% will be reserved for testing. And again, we won't look at the testing stuff at all for the training. They'll only be used afterwards. So we use this train test split to do that. We're breaking this up, so we'll have an X input for training and also then an X input for testing. So the X will be these 4 values, these 4 measurements. And then for Y, again, we have Y for training and Y for testing. So again, we've grabbed 80% of the flowers, and then the output, what we're predicting is just the category, one of the 3 categories here. So this is just the output we're going to try to predict. And we have that for training and for testing. Now we're going to set up our support vector machine and look to this. Now, if you haven't read through this section of the textbook, I suggest you do that. You might want to follow along here. And again, hopefully some of this will be review. We start with just a simple support vector machine and talk about how that works. If you remember from support vector machines, we might have 2 different types of flowers or categories, and we want to try to find a line that separates them linearly. So in this example there, again, doing the iris flowers, I have petal length and petal width, and this is one species of flower and this is another species of flower, and we can draw lots of lines in here to separate them. This purple line could do it, this pink line could do it, this green line wouldn't do it. That would, divide the blue flowers up, this versicolor flowers up into parts. So we have to find the right line. But not only do we want to just find a line, we want to find the best line. And so again, what we want to do is find a line that maximizes the distance between that line and the closest example iris here. So we talk about this, and again, you can read through the book and it'll explain kind of how it does this. And again, you just need to get a kind of concept of how this is. We're not going to go through any of the mathematics of how this works or derive any mathematical equations, because again, this is applied machine learning course. So let's talk a little bit about soft margin and hard margin classification. So in hard margin classifications, we require that we have a divider here, and we have one where all the flowers of one type are on one side of that divider and all the flowers are on the other side. And then here it's obvious, but again, sometimes if there are messy flowers in here, a lot of data in here, it gets to be very hard to do that when there are outliers in our things. So that's called hard margin classification. We won't be doing that so much. We'll be looking more at soft margin classification, and that's where we'll simply try to find the best. So again, we might have an outlier here, and then the question is, where do we put this line through here? Worried about this outlier, because wherever we put it, we're still going to probably get that outlier here. And so there's a parameter that you can set called C. It was called a hyperparameter because the parameters inside that we train inside the model are normal parameters. So the parameters kind of outside that we can set directly are called hyperparameters. So C is one of those. And again, we can choose the type of value for C. So if C is between 0 and 1, so with a low value C, you don't mind some margin, these violations. It's okay if you get some of these wrong. Where with a high value of C, you want to try very hard not to get these values wrong, and you pay a penalty for that. Lower values of C tend to be more generalizable models, but they don't always fit this. Okay, so we've reviewed some of that. Let's look back at the code here. So I'm going to set up our sport vector machine here. So this is our code for doing that. We create a sport vector machine model, and we use this. This is part of the scikit library. We just call this sport vector C, and that's for support vector classification. It's kind of weird that this is SVC and our models are usually abbreviated SVM. So SVC, and then our kernel, we're going to start with a linear kernel, just straight lines here. Now once we have that, we're going to train it. We just use that model up here, and we call fit. Fit will train it, and again, this should just take a sec to run. And then once we have it, we can score that model. So again, we reserve the test data. We can look at our test data and see how many of the test results were correct. So in this case, 93% of our test results were correct. So that's pretty good. We got 93% of the flowers identified correctly. Even these are the flowers we've never seen before with this. Now your numbers may vary with this model, because I'm going to go back up here. When we do our data split here, and we run this, different flowers will end up in our test and our training data each time. So when you do that, and then you go down here and rerun this, you'll get different results. So here I got 96% correct. So again, there is some randomness to the way we select our training data and test data, and that means that everyone will get slightly different answers for this. And we'll talk later on with some other models on how to smooth out that randomness. Okay, so then we're talking about soft margin classification. We just mentioned that in the book, and the C parameter. And so your job now is to answer a couple questions about the C parameter for this, and then run this code with the C parameter here. Now remember, up here we decided to leave that out. We don't need it, and by default the C parameter defaults to 1 here. But down here, we're going to run it again, but now we're going to specify a C parameter, and we can specify any value we want for this. So here we can run it with a parameter as 10, but we could also increase this to a value of 100 and run that. We could reduce this to a value of 1 and run that. So you can run it with different values and see what you get and explore that. So your job is to run it with a couple different values, record those, and then also look at this article and see. Now, remember, these things in their tasks, the questions in their tasks are just to kind of keep you awake and working on this. So remember, you have your write-up. You can click on here, but you probably have your own copy that you created in the start of Unit 1, maybe in Chapter 4. And you want to go to that, and there's the Chapter 4 answers. Hopefully you've already done those. And then you want to scroll down, and here's the Chapter 5 answers. So again, just go in here and say what you got for this. You got 93% here or something like that. And this is my sample. We actually ran this, and well, here, let's go do it. Again, you'll get different results here. I'm going to do this with 10 and run this. and I got 93% also there. Okay, and then you go down here to this next question, where I want you to read this Stack Exchange question, and let's see what I ask you to do. Read the second answer to this and describe in your own words why it might be useful for a higher or lower value of C. So again, I'm going to scroll down. Here's the question. Here's the first, or here's the second answer. The answer I want you to look at. It's got 175 upvotes, and again, it just walks you through this and has some diagrams showing different times where you may want to have a large or a small value of C. The C parameters and how that works. So again, just read that and put your answer in here just to think about, just a short paragraph, a couple, like a sentence, like 2 or 3 sentences should be good. Okay, so that introduces the C parameter for this that you have. Now we're going to talk a little bit about other kernels. Besides having a straight line, we can have a polynomial kernel. And we can look at that, and then there's another kernel we'll try after that. So again, here we've specified our support vector classifications, our SVM. Our kernel is now polynomial, and again, we can specify the degree and these coefficients. And we're not going to deal too much with these hyperparameters here. Just show you how you can set those up. We're going to look more at the next kernel after this. But again, they did this in the textbook. So let's go back to the textbook, follow along. So now they talk about nonlinear support vector machine classifications and how you might have some data like this and how do you get those to classify. And they talk about polynomial regression. And again, they set up a polynomial SVN here. With a certain number of degrees. Now, they set this up in what is called a pipeline, so that we can do a couple other things. So they're actually not, they're doing a linear kernel, but they're converting these to polynomial features. That generates more features and it does some standard scaling here. So this is one way of doing it, but it's not a very good way of doing it. So we're going to actually skip over that. And it talks about that, and we're going to go on and look at just using a polynomial kernel directly. So but again, we have this pipeline. Often we'll want to create a pipeline and feed a couple things through this pipeline. So we'll go through a standard scaler. One thing, support vector machines are kind of dependent on having a uniform scale between all the different features, and so running this through a standard scaler, we'll do this, and then we're setting up our support vector machine. So let's go back to our code here. And this one I don't have this using a pipeline, so this is not using a pipeline yet. Just sets up a polynomial kernel and do this. But then we talk about doing this with a pipeline. So here's our pipeline. And again, I'm not going to talk too much about a pipeline, but just know that what it does is it's just a series of steps that you feed your data through. So, and they're in order here. So we're going to go through a standard scaler, which will scale all of our inputs between 0 and 1. Let me jump back up. If you remember, our inputs weren't actually that bad. Let's see, where are the sample inputs here? Values, some of them, but this one was 5 centimeters and this one was only 0.2 centimeters. So there is some difference between there. There's not like 1,000 difference, but there is some difference there. So this will scale all these values between 0 and 1. Okay, so let's go back down here. Okay, a little bit. Oops. Okay, so here we're using a pipeline. We're going through a standard scale, and then we're going through our kernel. We're using a polynomial kernel of degree 2 with these coefficients in place. And then once we have that all model set up, we're going to fit it and we're going to test it. What's nice about setting up a pipeline like this is that when you train it and you're testing it, it puts both the training and the testing data through the scaler and the support vector machine together. So that's a nice way of setting things up. Okay, now there's another kernel called the Gaussian RBF kernel that we'll look at a little more. So let's scroll through our textbook again. So again, you can read through this and see some of the examples on how this works. And then we're going to look at this Gaussian RBF kernel and how that works. And again, we're not going to talk too much about the math of how this works and stuff. We are going to just look at some of the hyperparameters and how they are working. So we're talking about this Gaussian RBF kernel and setting it up here. And again, this code is, we're going to use this code directly in our examples here. And then we're going to have two parameters, a gamma parameter, and we're represented by this Greek gamma character and C. So, and again, gamma works on these bell-shaped curve for a different value. So a small value of gamma changes this. So we'll look at some differences with that. And here shows you some examples of this. So this kind of shows you the idea of different values of gamma and C again. So gamma tries to use kind of straighter lines and not have really wildly crazy curved lines here. So when gamma is set very low, it's basically a linear model. When gamma is high, like 5, you can get a nice curved model, and even higher, you can weave it in and out. So if you increased it even more, you could weave it more erratic. But again, a very high version of gamma will overfit your model to your data, and then your test data won't turn out so well. Here. And then again, same with C. Here's with a low value of C, and here's with a high value of C. And again, the value of C is how much we worry about the outliers here. And again, so with a high gamma and a high C, we're going to weave this around and make sure everything fits the data, even though it's we have lots of squiggles and stuff in here. Okay, so let's look at our model here. So again, we're using a standard scalar, and then our I have to go on after our questions. Okay, we're setting up our RBF stuff, and again, I've just skipped over the pipeline here. We could easily have done this in a pipeline, but just to simplify it, I've skipped that because I want you to just go through and look at this gamma and the C values here. And then we're fitting it using our training data and our training outputs, and then we're going to test it and see what % of the test flowers we have correctly, and so that's our score here. So you can set these to different values here. We can set this to a gamma of 100 and a C of 100 and see if we get it right. And again, with those values, while this would fit our training data real well, it doesn't fit our test data. In fact, let's try this out. Let me just put in a piece of code here. Okay, so normally we've been scoring this just with the test data here. But I also I just copied these two lines and put it in here again, and then used our training data here just to show you what that is here. And so again, here we're overfitting. We have really high gamma, really high C, and so we are actually getting, for our training data, we're getting 100% correct. There's no outliers. Every squiggle line is in there. But that means that these lines are going all over the place, and so this data we've not seen before, the testing data, doesn't show up very well. We only get 53% of that. Okay, so your job is to try it with a couple different values of C here, and then read this article about that. Oops, I forgot to change this. We actually want this for a couple different values of C and gamma, so I'll edit that. So I've got that up here. And you'll be putting in values of C and gamma here. I'll try to edit that. But then I want you to read this article here talking about this. This is just a different explanation because I don't think your textbook does a great job of explaining this. So this talks a little bit about this. Again, you can skip over a lot of this beginning code, and I just want you to get to the section where it's describing setting gamma to 100 and why that's not a good idea. And so I'm going to get down here. It sets up some sample data here and talks about linear kernels, and then here's our RBF kernel and talks about gamma and C and setting some gamma. So here's a gamma of 0.1, shows that results. A gamma of 1 shows that result. A gamma of 10 shows that result. And a gamma of 100, And see, that's the result we get with a gamma of 100. And that's why then when we get some test data in here, we may get some wrong, because we might get flowers in here, and it will think it's one flower rather than another for that. Okay, so your job is to read through this and describe this in your own words, what this is. And remember, you can just put that in here for that. Okay, I went through and made sure I got your questions here correct, so that it does have a spot to put in gamma and C for these different answers that you can try about. And that's all we're really going to be going over for this support vector machine. Now there's quite a bit left in this chapter, but we're going to skip those sections. So let's just show you what I mean. So there's a section on computational complexity, and again, we're not going to talk about that, but what order these are. There's something called a kernel trick, which allows some of these non-linear solutions to be mapped onto linear solutions, which speeds them up significantly, and the SVM's libraries usually do that for us. But again, we're not going to worry about that. Just note that there are some methods that make support vector machines quick when you're using a non-linear kernel. Again, we're not going to go through this regression. We've been using it just for classification, but you can also use it to predict a certain amount, predict a real-time value. But again, we're not going to go over that. And then they have this whole section under hood explaining how this works, how these lines are calculated. And again, if you've got a fair amount of math background, some linear algebra, you're feel free to go through this. But again, I don't think you need to understand what's under the hood in order to use support vector machines adequately. So all these sections and these theorems we're going to just skip over for this course. Okay, so that's the idea of this support vector machines. Hope you enjoyed it.